Now let us solve a problem where a mass is there on a rotating table. One table is rotating about its center and a mass is there on that table at a certain distance from the center. So this is a table, this is rotating about this axis, this is the top view, right? Turn it by 90 degrees and imagine the table, flat table, rotating like this. And this is rotating with an angular velocity omega, which says 2 radians per second. And there's a mass here, m, at a distance r from here, say this is 0.3 meters. And as this table rotates, the mass is rotating along with the table, right? So you understood the question? The coefficient of friction between the mass and the table is say 0.3. Mass is say equal to 0.5 kg. Question is, what is the frictional force between the mass and the table? That's the first part of the question. So how to find the frictional force? Yes, how to find? Use friction equal to mu s mg, right? That is the maximum friction. Maximum friction possible between this mass and this table will be mu s mg. Mu s is 0.3, mass is 0.5 kg, g is 9.8, and if you do the calculation, you'll get 1.47 Newton. This is the maximum possible friction between the mass and the table. But this much friction may not come into play, right? Whatever friction is required to provide the necessary centripetal force will come into play. Here the job of the friction is to provide the necessary centripetal force, right? So the friction that comes into play is equal to mv square by r, that is also equal to m omega square r, right? Friction provides the necessary centripetal force. M is 0.5, omega is 2, and radius is 0.3. So you'll get 4, you'll get 2 here, 2 into 0.3 is 0.6 Newton. And since this friction is less than 1.47, this surface, the surface between the mass and the table, can provide a frictional force of 0.6 Newton. So the answer will be 0.6 Newton. This is the friction that comes into play. This is the maximum possible friction, 1.47 Newton. But the friction that will be coming into play is only 0.6 Newton, and since this is less than this, the mass will rotate along with the table and not fly away. Right? Simple. Now the next part of the question. What is the maximum omega with which the table can rotate so that the mass does not fly off the table? Now you have to find omega maximum. So how to find omega maximum? Right now what happens? The maximum friction will come into play. And this will provide the necessary centripetal force. So F max will now be equal to m omega max square r. The entire frictional force will now provide the necessary centripetal force. The maximum frictional force will provide the necessary centripetal force. We have to find omega max. So what will omega max become? Omega max will be equal to root over F max, right, by mr. F max is how much? F max is 1.47, mass is 0.5, radius is 0.3, this will be a little bit less than 10. If you take the square root, you'll get the answer as 3.13 radian per second square. So we learnt in this question that when a body is there on a rotating table, the static friction between the body and the table provides the necessary centripetal force. If omega is less than the maximum possible, then the friction that comes into play is equal to whatever is required for centripetal force. So F is equal to m omega square r, and from there we got the answer 0.6 Newton. The maximum friction we found was more than that, and that was mu s mg, and that was 1.47 Newton. In the next part, we have to find omega max. When omega is maximum, the entire static friction will come into play. The maximum value of static friction will come into play, that is limiting static friction. So m omega max square r equal to F maximum. And from there we found omega max equal to root over F maximum by mr, and we got the value 3.13 radian per second square.